professors in its history who have occupied the chair of a university professor, but he has modestly not included that. He's included his affiliation to a company which he has set up in order to pursue novel and innovative ideas in the area of energy and sustainability. And in fact, he's the first occupant of a chair, the Academy Springer Nature Chair, which would support distinguished visitors in this area of sustainable development. He has 10 days in India, of which only 2 will be in Bangalore. And Bangalore is being kind to him. He's giving only 2 lectures here. But I think in Bombay, Pune and Delhi, he's giving 3 lectures. One intriguing aspect of his title is that he's not talking about the physics of molten salt breeder reactors, but the astrophysics. And in fact, to the world of astronomers and astrophysicists, Frank Shu is known as one of the most distinguished contributors to the subject. Tomorrow he will be lecturing on the Raman Institute on 6 decades of spiral density wave theory. And one of the pioneering papers was written by him with Lin in 1963, I think. And after that, he had a long spell at the University of California, Berkeley, and he focused his attention on the formation of stars and planets, and mentored a large number of graduate students and other students. In fact, his mentorship goes beyond the University of California. In the Joint Astronomy program, which runs in this institute, the very first year, the very first course of basic astrophysics, used his book, The Physical Universe, which he had just signed, as the textbook. He has also written 2 more technical volumes called The Physics of Astrophysics, extremely well known as a mentor and expositor and communicator. He moved, perhaps surprising many people, to be the president of Tsinghua University in Taiwan. And there is a historical personal connection there which he told us about this morning, that his father had been the president of the same university 32 years earlier. So perhaps he felt a sense of returning to some of his roots. In any case, that's the place where he apparently got very interested in nuclear engineering and in sustainable development in general, and he has pursued it. We are eagerly looking forward to hearing about these exciting developments. Reactors are not new, but the molten salt is both an old and a new concept. We'll hear why that's so, and seems to hold great promise, especially for our country, because it's based on thorium, of which there are abundant reserves in our country. So before I hand over to Professor Shu, let me just mention that following this lecture, we will have an event which has been arranged because of the fortunate coincidence of his visit here. And basically, the Astronomical Society of India and the Indian Academy of Sciences will henceforth be the joint publishers of the Journal of Astrophysics and Astronomy. And the first volume coming out under this joint banner will actually be released by Professor Shu. That will happen after the question and answer session following this lecture. We're waiting pleasantly.
Thank you, Rajaram, for that kind introduction. I was very pleased to receive this invitation to come to India, and especially to talk about this subject, which for many decades, India has been the leader in the field of using nuclear energy as its long-term, to satisfy its long-term energy needs, and in particular, to use thorium cycle for this purpose. I chose this title because I knew that the Institute here and the Raman group has strong effort in astrophysics, and I wanted to use it as an example of how astrophysicists can contribute to what is perhaps the greatest challenge of this century. I hope to show you that these ideas that are well known in most part to nuclear engineers can in fact be unified from what we know in astrophysics, okay? Although they don't think this way, in fact, one can obtain a more unified outlook, and in some sense, a simpler outlook, by looking at it from an astrophysicist's point of view. So, in particular, I will talk about the role of graphitic technology, or carbon technology, in this subject of nuclear reactors as a construction material for a nuclear reactor. This is, we call these two-fluid molten salt breeder reactors. That's an acronym up there. And basically, in the typical nuclear reactor, not only do you have to have a medium to perform the chain reaction, but you have to have some medium to carry that is generated. So in this case, the salt that carries the fuel goes down here, meets the bottom, comes back up. But you could have other arrangements. And then in channels that are going this way, without intersecting these channels, you have the coolant, okay, passing it so that the heat generated by chain reaction is passed to this blanket salt, which carries thorium, irradiating it with neutrons that converts it to a new fuel, Uranium-233, which can then be put into the fuel salt cycle. And it was Baba's fundamental insight that this was especially appropriate for India's future. Now, of course, if you have liquids flowing through here, you must make sure that it's sealed so that the two salts don't mix. Otherwise, you lose the advantage of keeping and the thorium separate. So you must be able to seal graphite, which usually has and is porous. Okay, so you must be able to seal it so that the two. And this was sort of known to Oak Ridge researchers. We their suggestion and found that we could indeed seal it with carbon. Why carbon? Evident shortly. Okay, basically carbon can slow down to not absorb them. And here is a piece of graphite in molten floor. So every astronomer immerse a black box, let it equilibrate. It will radiate, typically in the near infrared and some red part of the spectrum. So you can see it's glowing red, but the utility is that it's not destroyed. No, that salt is highly corrosive, so the test tube is completely different in this experiment. But if you look at the, you wash it, there's been any attack. Playing from the graphite is especially good medium. Anyway, this was one of our HX team. HX means heat exchanger. They are largely some classmates of mine from whom I convinced they're now retired. They can do good as well as be successful. And then other people in the astronomy community. I think many of you know Paul Ho, Ruben Krasnopolsky, as well as from Hong Kong and Michigan and other places. Anyway, that's doing this work. Okay, so here's the outline of the talk. We all know, of course, that current economy of the world, 80% is powered by the burning of fossil fuels, and that side effect, the level of greenhouse gas, carbon dioxide. This is a problem that is easily explainable to astronomical audiences in terms of the infrared absorption of light by a carbon dioxide in the atmosphere. Anyway, I'll focus here in this talk at Bangalore on half of the technology that we're developing to address this. So this is a nuclear power for generating electricity at this place. And at the last day of my talk, when I'll be at Delhi, I'll talk about a similar technology using molten salt, where you immerse biomass directly into the molten salt to carbonize the biomass, locking it up so it does not rot. And if you don't burn it, but use it in other ways, it becomes negative emissions. It's like, you know, if you were to make coal out of the air via plants and then don't burn the coal, but put it back into, you know, coal mines, that would obviously reverse climate change in a very safe way. In fact, there are other uses that are even more beneficial to the economy, okay? I'll talk about that in Delhi because I hope to convince your government that this can help solve the environmental pollution problems that now face Delhi from particulate emission. Our way of doing things has no such emission. When we talk about nuclear power, of course, most astronomers think of thermonuclear fusion. I want to make it clear that I'm talking about fission, not because I don't believe fusion is the long-term future of humanity on Earth, but because it probably cannot come online in a commercial way in time to save us from climate change. So this is a stopgap measure. It can, if needed, power the entire world needs if you use thorium instead of uranium, you know, for, as Baba pointed out, more than 400 years, okay, maybe thousands of years, if you're willing to go to low-grade ores. Anyway, India itself has lots of thorium, very little uranium, and so India has a very long head start on the rest of the world in thinking about this problem. That's why I was so anxious to come here and talk to people, the world expert on this. I will do so-called SWOT analysis, discuss the strengths, weaknesses, opportunities, and threats of this traditional way of doing things versus this new way. It's not really new. Roger mentioned, it's been brewing since the 1950s. But for many people, this is a new way of doing nuclear power. Whenever you talk about nuclear fission power, you have to discuss four concerns that society has. First and foremost, not among scientists, but among politicians and the general public, is it affordable? Is it superior? So think of four, and since this one has a dollar sign, is it superior? Or more practically, can you produce electricity cheaper than from burning coal, or in the United States, natural gas, which has lots of natural gas. I hope to convince you there are good reasons why one that it's physically impossible to release large amounts of radioactivity to the environment. Right now, the strategy is called defense in depth, which is used in the nuclear industry and also in space applications, where if you need one critical piece of equipment and you're afraid it might fail, you build not one, but 3 or 4 of them. Well, automatically that has a corollary of everything costing 3 or 4 times more than if you just built one. So we take the point of view that safety should be approached from physics, not from engineering. That is, it should be intrinsically safe so that physically it's impossible for these large-scale releases to occur. And then finally, I'll give some take-home messages. So let's start with fission, not fusion. Shortly after people discovered the existence of the neutron, it was realized that these particles could enter the nucleus of atoms without impediment, without repulsion by the charges that they carry, because they carried no charges. And so people immediately realized this was an easy way to induce nuclear transformations. And they accidentally stumbled on, this was pre-World War II discoveries in the 1930s, that one of the interesting things was when the nuclei got heavy enough, it could be induced to fission, okay? But there's this myth today that fission is somehow unnatural, and that fusion occurs in stars, but fission does not occur in nature, and therefore it's bad, okay? That in itself is a questionable deduction, but I want to dispel it, that in fact it did occur in nature, all right? And I think many of you may know this, so I'll go through it quickly. But basically, in the 1970s, an interesting event took place. France, of course, uses a lot of uranium, and they have uranium mines in Africa that they ran, in particular one in Gabon, where they noticed that a shipment to France was missing some uranium-235. Usually, it's about 0.7% of natural uranium. The rest is uranium-238. But some of it was missing, and they were afraid of theft. But when they finally traced down where this uranium came from, it came from a site that contained this natural fission reactor, okay? And they made a positive identification by analyzing the isotopic composition and found fission products, things that have undergone fission with an isotopic signature that was only associated with fission having occurred, okay? So why did this happen? Well, you can date it because you have radioactive substances, and the date was found that these reactions occurred about 1.8 billion years ago. Now, those of you who know about uranium knows it's composed, natural uranium is composed of uranium-235, which decays with a half-life of only 0.7 billion years, whereas U-238 decays with a half-life of about 4.5 billion years, which is about the age of the Earth and the Sun. So uranium-238 has fallen roughly by half since the formation of the solar system, but uranium-235 has fallen much more, even though they started nearly equal, in fact, with uranium-235, probably more abundant than natural uranium, U-238. By after, from 4.5 billion years ago to 1.8 billion years ago, uranium-235 had decreased to where it's only about 3.2% natural uranium. Today it's decreased down to 0.7% of natural uranium, but then it was 3.2%. Now it turns out that at this time, an interesting happened in the Earth, that is the appearance of organisms, algae and the like, turned an atmosphere that had no free oxygen to where it had appreciable free oxygen. Now uranium is a metal that can be either +4 or +6. And +4 and +6 are quite different, okay? UO2 is not soluble in water, but UO3 is soluble in water. So you can imagine what happens. At this point, some of the UO2 became UO3, and if water flowed through this area, it would carry it into this pocket, which you can see is roughly spherical. And that's an ideal configuration for a nuclear reactor because it has the most volume for a given amount of surface area. So the losses are minimized when you have something of a given volume when it's a spherical. So it carried it there until the concentration increased even above 3.2%. Now, it turns out 3.2% is what we consider lightly enriched uranium today. But then it was just a natural abundance. So when water carried it to this place, there was enough uranium-235 to reach a critical mass, and so a reaction occurred. That released heat, and if it got hot enough, the water would be evaporated. Now, water turns out to be an excellent moderator in slowing down neutrons. Why that makes a critical, decreases the critical mass, we'll shortly explain, all right? But anyway, just accept this fact. So the reaction occurred and drove away the water, so now there's no more hydrogen mixed in there that slows down neutrons, so new uranium flowed into here. When you assemble the critical mass, it shot up again. In this way, people are able to show that several incidents of on-off operation at sort of kilowatt levels, this is very small for a nuclear reactor, kept on going for millions of years. Okay? So what lessons can we learn from this experiment that was carried out by nature 1.8 billion years ago? Well, first, the light water reactors are intrinsically safe against the most feared accident, which is the loss of coolant accident. So water helps to carry the heat away, but if you expel all the water, then the coolant disappears, so you're afraid the reaction will run away, but because the moderator has disappeared, you don't have things slowing down neutrons, so the critical mass is increased even more, and it actually shuts itself off. So that's why light water reactors are very safe against continued reaction. But of course, there's decay heat, and that's what creates the problem today. That is, even if you shut off the reactor, you still have to carry away the decay heat. But if you operate at low levels, at power levels, so that the decay heat of the fission products is not enough to melt the core, and something like rock is very hard to melt, then you don't have to worry about that too. So one of the lessons is don't operate nuclear reactors at higher levels, and you can carry away the decay heat easily. The third is that the fission products, which people are so scared about storing in geological settings, is not a problem. Nature could do it, and they didn't wander far for billions of years. Okay? Geological storage is possible where the fission products do not migrate. Okay? So a lot of the myth is dispelled. There were no nuclear operators around. There was no governments around, no regulatory agencies. Yet nature performed this experiment over and over again. This is probably not the only such place, but it's just one that was, where you could interpret all the hints. Okay, so let me now talk about superiority. And this slide is what I call the HR diagram of energy. Everybody knows what the HR diagram is in astrophysics, right? It's a vertical axis, a horizontal axis, where everything is backwards as far as physicists are concerned, because astronomers like to put the important thing in the denominator, okay? So this is the number of joules per liter of various kinds of energy, okay? So the smaller, for a given joule, the smaller the denominator, it increases to the right. And that's good, because it makes things small, you can build compact equipment. This is joules per kilogram, and that's good, because that determines how long you can use this fuel, and since kilogram is again on the bottom, the smaller the number of kilograms to produce a joule of energy, it increases this way, which is again good, sorry. Okay, so this is what I call the natural hierarchy of energy in the world. And all physicists and astronomers can quickly explain this. Namely, when we talk about mechanical energy, let's say wind, a typical speed might be 7 meters per second. That's like 20-some kilometers per hour, okay? That's a pretty healthy wind. Sight is considered good. And so if you have something which is some meters per second, if you have a joule of energy, how much space does it occupy? Well, it's air, so it occupies quite a bit of space. It's over here, all right? That's what mechanical energy is measured It's joules per kilogram, 10 to the minus 2 joules per liter. If you talk about hydroelectricity, you're talking about water, which is 800 times denser than air, and you can make it fall, typically, over 100 meters. So every physicist knows how to calculate. If you drop something over 100 meters, what kind of speed it uses. I'll let you do the calculation yourself. It's much faster than 7 meters per second. So wind is beat by hydropower by several orders of magnitude, okay? Well, I think the physicists know, I'm not sure every scientist knows, but electricity is essentially equivalent to mechanical power. You can convert electricity almost with 100% efficiency into mechanical power, but electricity is also close to chemistry. You know, electricity is part of chemistry, so it's not surprising that, you know, it falls sort of in between. A supercapacitor, for example, falls in between batteries, which are basically chemical reactors that converts chemical energy directly into electricity. So here's a lead-acid battery. All these are rechargeable. So this is what you have in your car. This is a nickel-cadmium battery. This is what you have in your cell phone. This is a lithium-ion battery. You can see, you know, within factors of a couple, they're more or less the same. So although, you know, when it comes to economics, a factor of 2 is important, on this kind of logarithmic scale, you know, they're sort of all bunched together. Here's chemical reactors. So even wood is better in this sense than chemical batteries. Coal is better than wood, gasoline is better than coal, and natural gas is better than gasoline. All right? But natural gas is, of course, usually not a solid or a liquid, which is what's over here. It's usually a gas, and a gas has much less density. So if you liquefy natural gas, it's over here. If you let it just take its natural state, which is methane at standard temperature and pressure, it's over here. So it's much less compact. This is why natural gas, except in the United States, is not such a wonderful fuel. By the time you liquefy it and ship it from the United States to Asia or to India, or from Russia to India, you know, it's huge pipelines, huge tanks to store things. You can't store them as well as you can store coal. You can put a big pile of coal at your plant, so that's why people use coal more, all right? So easily understandable. Hydrogen's a great fuel, but where do you get the hydrogen? Moreover, it's also a gas. It's a gas that's much harder to contain than methane, because very small molecules, easily diffuses even through metals, okay? That's why people don't make dirigibles out of hydrogen gas anymore. Just too dangerous, okay? Where's uranium and thorium? It's up here. 14 orders of magnitude better in compactness of equipment, 12 orders of magnitude better than wind, okay? That's just simple facts of physics. So you can ask, how is it possible if this diagram is right, and I invite you to calculate it yourself, how can it be possible that wind is competitive with other forms of generated electricity? That's a deep question. Although, you know, a factor of a few improvement in technology you can explain, but 14 orders of magnitude? Well, it is possible. It's a fact, all right? And the reason is because all of these things, especially over here, not here, you need, when you burn them or you react them, you get heat, which is not electricity yet. To generate electricity, the best way is through a turbine. So you cause a gas, or sometimes something else, to flow, because it expands as it flows, and it turns a magnet around the coil of wires, and from Faraday's law, we get electricity. Well, that piece of equipment is much bigger than the reactor. So it costs a lot more to build that piece of equipment than the reactor. Okay, so that's one explanation why wind can compete with these things over here, because this is all turbine, all right? So all your money is spent building the turbine. Over here, it's almost all spent building the turbine, so that's why it will cost as much or more if environmentalists oppose this technology. Okay? Why is uranium and thorium, still much better yet? It's because although you can build a reactor very small, let's say in a nuclear submarine, you still got to get the heat out. And a simple fact of nature that getting heat out, we usually use thermodynamic engines, and there's a limit to how small you can make these things and turn heat into motion, which you turn into electricity. It's roughly your car engine. Everybody knows if you look at how powerful your car is, you know what, maybe 100 horsepower. If you have a big fancy car, a few hundred horsepower, and it's a cubic liter of displacement, right? Well, that's about the energy density. And it doesn't matter whether your nuclear reactor is burning nuclear fuel in a much smaller volume. Ultimately, you got to get the heat out, and so the nuclear power reactors also have the same power density. So they're not much better than these as far as getting the heat out goes. And when you consider the other factors, then they become worse because people insist we cannot have any accidents. You say you put in 3 pieces of equipment where you only have one, but you cannot guarantee that you have no accident. So the bars, every year, nuclear grows more and more expensive. So what's the way out of this vicious loop? Well, you obviously need a better turbine, okay? A turbine that only nuclear power can use effectively. And I'll talk about that shortly, okay? So this is a summary. Wind is competitive because it's all turbine. Although nuclear fuel is incredibly energy dense, thermohydraulics still limits the conversion of heat into electricity or kinetic energy. And that makes sort of as a great equalizer. So here's the new technology. Surprisingly enough, companies are looking into storing not electricity, but heat, because storing electricity through batteries is very expensive. It's also not a clean technology. So they're looking into storing solar power as heat in the form of molten salt. That's a connection, which has a large capacity for heat because it's a liquid density, and it has other good properties. So is there a way to combine this in a turbine situation where you have a big advantage? And the answer is yes. This is built, this case, but other people are working on it, by General Electric. It's called the sun rotor because they want to have convert sun into rotary motion, which generates electricity. And here's a 10 megawatt electric turbine. Now, those of you who know about wind turbines may know that the largest ones that are being planned are as tall as the tallest building in Bangalore or Mumbai or Delhi, okay? And they generate about 3 megawatts. So this is 3 times more. How big is this? Well, this is a meter stick, so it's about this tall. How thick is it? It's about something that you can hold in your hand. It generates 10 megawatts electricity. So it's a tremendous advantage over having to build something as tall as a giant skyscraper, okay? So what is the working fluid? It's carbon dioxide, all right? But not in its natural state as a gas. If you burn natural gas, the carbon dioxide you get is a gas, so it's not very dense, even if at high pressures. It's in a supercritical state, okay? Those of you who remember your theory of imperfect gases know that when you subject many gases to a high enough pressure and a high enough temperature, you can reach a state where you cannot distinguish. There's no difference between the liquid state and the gaseous state, okay? So critical carbon dioxide, where the temperature is higher than 400 C and the pressure is 100 bars, 1 bar is atmospheric pressure, it's high enough to lose the distinction between gases and liquids. What does that mean? It means you can expand this supercritical carbon dioxide like a gas to create a flowing fluid with almost the density of a liquid. Not quite, but within a factor of 10, the density of a water. So you can now easily see why this turbine is so powerful, because if you've ever ridden on a jet plane, they use turbines to generate power, and they're not that much longer than a meter, maybe 2 meters. So the length is just, that's how much time you need for to do things. But the inlet can be much smaller because it's not gas at atmospheric pressure when it flies at great height, at even lower pressure. It's something that's 100 times more dense. So, this area can be shrunk by a factor of 100. That's why. It's kind of simple. Once you explain the basics, you can see how it works, okay? So you just imagine the power of a turbine of a jet plane. So obviously, natural gas is not easy to use this kind of turbine yet. It's the coupling between molten salt and supercritical carbon dioxide that really makes it possible. And although this is a difficult calculation, most people's estimate is that you get electricity, which is so-called dispatchable. That is, it turns on when you want it to be on. You can turn it off when you don't want it at half the cost of coal or natural gas. So this would be the incentive, lower people's electricity bills by a factor of 2 and make it reliable, not only available when the sun shines or when the wind blows. Okay, so let me talk about sustainability and security. This is really talking to the converted, because everyone, I hope, knows that your first chairman of the Atomic Energy Commission in India envisioned this proposed in 1954, when people were just barely thinking about using atomic power for in the civilian sector. Dr. Bhabha already proposed at a conference attended by Prime Minister Nehru a 3-stage vision of making India self-sufficient in energy for 400 years, okay? Probably longer. Thorium is a very abundant energy source if you can utilize it. So the first stage was to use pressurized heavy water reactors. Why heavy waters will shortly become obvious to everybody who studied Big Bang nuclear physics, to burn natural uranium to produce electricity and spent nuclear fuel. So because you have uranium-238, some fraction in today's reactor will become plutonium-239, and that's a fuel, whereas uranium-238 is not. Then the unfortunate thing is that India doesn't have enough natural uranium to jump directly to here. So he proposed, this is considered nuclear waste. So another way of saying is, sorry, India, you don't have enough nuclear waste. It's not a bad thing, it's a good thing. So he proposed fast breeder reactors that would produce more uranium-235 than they burn to convert those excess neutrons, thorium-232, to uranium-233. I put a red cross bar through here because I believe people in India are considering whether it's possible to skip this step. Dr. Bhabha was a little optimistic about how long this would take, but under the leadership of people who followed him, in particular Dr. Kakadar, who is now was the second chair of the at BARC, was led through this, and I think people are beginning to skip this step. I'm hoping to convince you that the best way to skip this step is, in fact, with molten salt breeder reactors. Okay, so let me now explain from first principles what the idea is. First, there are heavy nuclei that have an even number of protons and an odd number of neutrons that are so-called fissile. That is, a neutron that is absorbed by such nuclei, no matter how fast or slow they come in, can cause it to split into two fission products with the attendant release, of, how do I go backwards? With the attendant of release of 2 or 3 neutrons. So that was critical finding, okay, in the 1930s, that these fissiles. The reason is simple. Everyone knows that protons and neutrons are fermions, not bosons. They have half-integer spin, and therefore the lowest lying state usually finds them in paired configurations. If you have an up one, you have a down one. But if you had an odd number of neutrons, it's clear at least one of them cannot be paired. So therefore, if you send in, suppose it's up, if you send one that's in down, you will release 1.5 MeV more energy than needed by the nucleus, or can be used by the nucleus. And so that extra energy goes into vibration of the nucleus, all right? And it was explained by first Lise Meitner and their nephew, Frisch, Otto Frisch, and later in detail by Niels Bohr, that the things, when they separate like this, you have 2 positive charges which are pulled further apart than normal. If the protons, the positive charges, repel more than the attractive nuclear forces try to pull them back together, then they can vibrate apart. And it was this insight which led to the notion that E equals mc squared occurs in these reactions. In fact, E equals mc squared explains all reactions. It's just in these reactions you can actually see measure the mass difference. So there's 2 ways of thinking about where the energy comes about. One is it's actually electric repulsion, changing potential energy into kinetic energy. So you gain about 200 million electrons per fission. The other way of thinking about this is just to measure the masses that, after they become separated, compared to if you bring them to rest. And those masses are more because they have kinetic energy, and that's also 2 million electron volts of energy. So that's why E equals mc squared. Energy, in some sense, is an ability to transform matter. Whether you take nuclear energy and transform it to kinetic energy, or you transform kinetic energy to electric energy, it's all E equals mc squared. Okay? All right. So uranium-235 is 0.7% natural uranium. Now, there's all these things, I said, produce 2 or 3 neutrons. Here's what they release on average. It's a statistical process, so there are fluctuations about this average, but average over typical conditions. Plutonium-239 produces, as you can see, nearly 3 at low energies and in excess of 3. So this is the best except for competing reactions. Plutonium-239 can also absorb a neutron and not fission, all right? Become plutonium-240. All right, 240 is even, so it's not fissile. All right. However, occasionally it can spontaneously fission. So it's like 240 is a convict that should be in jail. So if you put a prisoner into jail behind a tall wall, typically they can't jump over the barrier. Classically, they can't. But quantum mechanically, they can tunnel under, okay? Many prisoners have tunneled under wall. So that's what happens. It's a fission process that's waiting to occur, but you can't control it. It comes out probabilistically when it can. So it's a nuclear deterrent, because if you try to build a bomb with plutonium-240, some of it will spontaneously fission, giving you a chain reaction before you're ready, and the bomb explodes before you're ready to trigger it. So that's, as we'll see, a deterrent. U233 has a different path to deterrence. But anyway, U233, you can see, has less neutrons at low energies and less at high energies, but it has a better branching ratio. 90% of the time, when it captures a neutron, it will fission. Only 10% of the time will it capture a neutron and not fission, become U234. That's not fissile, so then you have to capture another one before it comes U235. So you've wasted 2 neutrons right off the bat, right? If you go that path. But fortunately, that's not very likely. U235 is somewhere in between. Plutonium-239, roughly speaking, 60% will fission, but 40% will just capture the neutron. Now, here's the cross-section. I'm sorry to use this technical phrase, but physicists shouldn't be afraid of it. You can see that the cross-section for this reaction to produce a fission in U233 is very high at low energies, and it drops. This is a log-log plot, so you all remember a straight line and log-log plot is a power law. It is e to the minus 1/2, all right? This is the energy of the incoming neutron. Why is it e to the minus 3/2? That's very simple. Nuclear forces, especially involving the neutron, is a short-range force. So it's only effective while the neutron is passing through the nucleus. But atomic nuclei all have about the same nuclear density when you get to high atomic numbers. And so it takes us more time if you're going slowly to pass through the nucleus than if you go fast. So your chances of a reaction are better. And the time that you pass under these conditions is just inversely proportional to the square root of the energy. But you can see that in addition, there are these, there are these resonances, okay? Whenever we see this spiky things. And that's because it's not, the nucleus is not a single body. It's made up of many, many neutrons, many protons. They all interact with this incoming neutrons, and sometimes you can hit a resonance, okay? I like to tell students if they ever play billiards or pool and you try to break up a pack, if you shoot very slowly, there are many ways in which this ball can collide with that ball once you get into the pack to absorb that ball, because they just transmit around. And you know, when you play safe, you only knock out 1 or 2 of the pack that you get. So it's the same thing in nuclear physics, except with quantum mechanics, complicating things. So you can see this general pattern. It's a power law with larger cross-sections at small energies with these spiky resonances at keV kind of energies. But the width is very small. So it's not quite as simple as I explained, but roughly speaking, that. And you can see even the capture that produces uranium-239, which will then beta decay twice to give you plutonium-239, has the same kind of pattern. Of course, what happens at high energies is quite different. Okay, whoops. Let's see. I guess I'll just leave it this way. You can see that it drops off, whereas these level off. And these fast neutrons, of course, are the basis of fast nuclear reactors and also weapons, okay, for fissiles. The fact that the cross-sections flatten off. Okay, so what happens? Well, why thorium is a much better fuel than uranium is the following. Natural uranium is mostly U235. But as I said, U235 has a significant chance of capturing a neutron to become uranium-236. Typically, it will just sit around until it captures another neutron. So it goes by this process where it captures neutrons and goes up in neutron number, but not in proton number. Occasionally, it will reach a short-lived state and then decay. But, you know, the U238, for example, that accompanies U235, the natural uranium, will become U239, will go this path, then it will go this path, and then this is long-lived enough that it sits around and captures another neutron. It can go this way, and then it can branch. It can do all sorts of things, including alpha decay. So when you use uranium-235, that's U-238, it becomes a mess. There's all sorts of things here. And that's why it's so hard to use spent fuel, because what you have in your fuel depends on the reactor that you built, depends on how long you've stored the fuel, and if you use solid fuel elements, it's very hard to reprocess. That's why building fast reactors is not very easy, okay? But if you have molten salt, you see, it becomes easy. It becomes easily homogenizable because you put it into a liquid. When you pump it through the system, it becomes turbulent in the mix, and you don't have to know what the homogenization is. It will occur automatically, okay? That's why one of the advantages of using molten salt reactors, even for conventional burner or converter reactors. Now look at thorium. Thorium only has one stable, naturally occurring isotope, which is uranium-232. There's no isotope separation or anything like that. It will typically capture to become thorium-233. That decays very quickly to this state, all right? And then this has a half-life of about 2 weeks. So this became a controversy between Fermi and Wigner as to whether you would capture another neutron that would waste a neutron, and then you'd have to, get up to here and then decay over here, perhaps, to U-235. But you would waste neutrons, which you can't spare easily. But if you're lucky, the thing will decay into this state, which has a high probability of fissioning and only a 10% probability of going this way. Once you get to U-236, it has such a small cross-section for doing anything that basically that's a dead end. Okay, so this sort of explains things. Now, uranium, you will recall, is an element. It behaves very differently, whether it's valence state at +4 or +6. UF4, so it's +4, is a solid at low temperature. It can become a liquid at high temperatures, but it's very hard to turn it into a gas. UF6 is a gas if you're at low, ambient pressure, if you're above 55 C. So once you have a gas, you can do many things in addition to centrifugating it to separate the isotopes, etc. That's typically how it's done. That's what Iran is doing to build its atomic weapon program. It's very costly, so India wants to avoid this step and just be able to use natural uranium. There are only 2 moderators that can use natural uranium and get a chain reaction. One of them is use heavy water, replace ordinary hydrogen with deuterium. Why deuterium? Because in the Big Bang, it already ate its neutron. So it doesn't like to eat another neutron. If it eats another neutron, it's tritium. Tritium is a very unstable thing, so that's not a high branching ratio. It does happen, but not often enough to cause any problems, okay? So that explains it, right? In fact, you can generalize this. In astronomy, in many environments, like the Big Bang, many reactions are initiated by neutron captures, either in the Big Bang or in late stages of stellar evolution, okay? So in all those environments, if you have 2 isotopes, usually the lighter one is not good. So lithium-6 is produced in the Big Bang, but it immediately leaves 7, okay? So where does lithium-6 come from? Well, it comes from cosmic rays breaking up things. But that lithium-6 exists today, and you wouldn't like to use it in a nuclear reactor because it has a very big cross-section to eat a neutron. So understanding like this helps you to understand the problems, okay, that people have in the whole cycle. So carbon-13 doesn't exist because carbon-12 likes to eat a neutron. No, it got there by some completely different path. Similarly, oxygen has 3 isotopes. And if you look at the astrophysical origin of oxygen, you know, oxygen-16, that's easy. You have carbon-12, you capture another alpha particle, that's oxygen-16, major pathway. Oxygen-17, less likely, but it's not from oxygen-16 capturing a neutron. oxygen 18. Also unlikely, okay, from 17. So those guys can be used in nuclear reactors, but they're the exception rather than the rule. Okay, so I'm just telling you this as part of why astrophysicists easily understand why nuclear engineers do what they do. Okay, so what is the barrier to the U233 cycle? Well, you see, when a fast neutron comes in, if a slow neutron comes in, most likely to do this, but a fast neutron can actually come in and knock out 2 neutrons. So it goes this way, all right? It's the same target, so it's unavoidable. If you can go this way, and your nuclear reactor has both fast neutrons and slow neutrons, I should have mentioned, when you fission, the neutrons that come out are fast, okay? Typically MeV kind of energy. And that, when you get to 5 or 6 MeV, can have this process of knocking out 2 neutrons. So you go this way, then this is called the R process. You add a neutron rapidly enough before it can decay. This takes, the age of the universe to decay, so that's easy. But this one decays relatively quickly. The protactinium-231, which stays around long enough, so you capture this, and then you go to this. But because the crucial step is this first step, if you can go this way, you can also go this way. And with the reactor that I'm proposing to build, the ratio of what you create in 232 compared to 233 is just a ratio of the cross sections of these 2 guys on the same target, okay? So once you tell me what the reactor is, you can calculate the ratio of this cross section. And it produces a concentration, which is about 29 parts per million. To be considered proliferation resistant, you have to be above 5 parts per million. Why? Because uranium-232 is a long-lived nucleus, but it decays by alpha and beta decays. And the last step of that decay will produce an energetic gamma ray. If you know astronomy, you know gamma rays are the most penetrating of all electromagnetic radiation. So penetrating that if you have enough of it, if you try to assemble a bomb, it will kill the worker in half an hour. This isn't enough to kill them in half an hour. It will make them very, very sick. Even if they don't make them sick, they will destroy the electronics that you typically need for the timing of the trigger of the bomb. Or if that, you could build a radiation-hardened timer, it's very easy to detect, a Geiger counter. You can't even ship it into a port in a big container without a simple Geiger counter finding it. So it's considered very safe. I can just say as a practical fact, no nation on Earth, including India, including United States, including Russia, has ever constructed a weapon completely out of uranium-233. They've built some that are hybrids with plutonium, but so much easier to make bombs from plutonium than from U-233 that I think it will not add to the proliferation risk. So what does our design for nuclear reactors look like? So this is where we differ from Oak Ridge National Labs. They originally also thought of building what's called a 2-fluid molten salt reactor, but then they had a breakthrough where they could put the thorium in with the uranium and just have 1 fluid, and that's the one that they ultimately proposed. That has many problems, all right, including chemistry to reprocess the fuel. You really like to keep it different because, unfortunately, thorium behaves very similar in chemistry to lanthanides, and lanthanides are very abundant in the fission products. So you put it in a fuel that has fission products, you have a difficult separation that faces you chemically, all right? Very hard work. So nobody knows how to do that. So today, most people that talk about this look at 2-fluid reactors. So what kind of a reactor should we build? So I'm a physicist. I say we should build a spherical one, just like nature built, okay? People say, spherical nuclear reactor? All the pictures I see are cylindrical. Isn't it hard to make a spherical reactor? No. The first reactor that was built working reactor was Fermi's reactor. He built it in a squash court on the campus of the University of Chicago for the same reason that all physicists considered a sphere before anything else, especially astronomers, right? Because it has, it's the simplest geometrical object that's closed, okay? It has the least surface area for a given volume, so your losses are least. So how do you define a sphere? You just define it by wherever you have moderators. Where you don't have moderators, you don't have nuclear reactions going on. So the idea is just to put a cap on it, which is spherical, some kind of net made of carbon fibers, perhaps. And then you load in between these pipes that carry the fuel salt, the uranium, the fuel, through the region that has graphite balls floating in here. They float in molten salt, so they will float, and you just add enough balls so that the bottom defines the other half of the hemisphere, okay? So that's easy. Use these graphite balls. It's modular. I haven't told you what the scale is. You can put as many pipes down as you want. You can make this as big as you want. You can't make it as small as you want because you have to have a critical mass, okay? So typically the reactor that I've studied in detail that will produce 4.6 gigawatts of thermal power, of which roughly half can be turned into electricity, you would need this diameter to be 6 meters. You want half a meter here and half a meter here, where you irradiate thorium, so 7 meters here, 7 meters. So this might be a cylinder, but basically this thing you want is to be a sphere because it makes the calculation much easier. We don't want to do supercomputers calculations. What other people take 4 months to do on a supercomputer, I can do on my computer in 2 days because I'm not that good a computer programmer, okay? But once you make it a sphere, you can do all sorts of things. And I'll tell you what some of those things are, okay? So this kind of way of building a heat exchanger is called a tube and shell heater. This is a shell where you carry one kind of fluid that carries away the heat. This is the tube where you carry the fuel that carries away the energy. The energy is released here in fission fragments. They collide against the walls. Then you have to transfer it by heat conduction across the walls to where you have the blanket salt, okay? So the blanket salt not only contains thorium debris, but it is used to carry away the heat. This is called a tube and shell, and it's known to engineers. This is the most efficient kind of heat exchanger if you want to transfer heat from the fuel salt to the blanket salt. What is the temperature of these two? These are controlled by how hard you pump the two fluid. Let me explain this, okay? It was this feature, which when I understood it, when I first read about molten salt reactors, that told me this was a great reactor, because that's exactly how the sun works, okay? So let's think about why the sun doesn't need a nuclear operator. You say, well, it's fusion, not fission. That's not the important part. Fusion reactions are also temperature sensitive. If they run too fast, the temperature will go higher, which will make the reactions go faster, okay? So why doesn't the sun blow up? The answer is because it's a gas. When you add heat to a gas, it becomes hotter, it expands. You expand a gas, it cools it. It cools it more, then the reactions go up, so it controls itself. It needs no operator, all right? Similarly, if you don't have enough, it's too cold, it will contract until it has enough, okay? That's what in astronomy we call, negative temperature heat capacity, okay? In nuclear engineering called negative coefficient of thermal reactivity. Same thing. Here you have salt. It's a liquid. But liquids will expand if you heat them. So the same thing will happen. If the heat gets too high here, it will expand out of the region where you have moderators. So it lowers the mass of fuel that you have available. If you don't have enough, it will contract. So it depends on how fast you pump these two, maintaining the temperature difference, which determines how much heat you can transfer. Now, This was recognized early on. In fact, the reason Oak Ridge was commissioned to build this reactor was because the Air Force in the United States was jealous of the Navy. They had nuclear submarines. They could run a long time under the ocean. They wanted bombers that could fly around for months at a time, okay? Because, you know, during the Cold War, that was important way to have deterrent. So you can imagine what the demands are on an airplane. If it dives, you need to be able to get power whenever you need it. This will deliver you power. It will give you power when you need it. Just pump harder. Make this colder, you transfer more heat, this thing will produce more reactions, and that's exactly what you want, okay? So, nuclear reactors, if you build them well, will not have runaway nuclear reactions, right? You have to guarantee that. So the thing that you're often afraid of is loss of coolant. Well, if you lose the coolant, suppose this tank that holds the blanket salt develops a leak and you somehow lose it. Well, first of all, it's self-sealing, because the only reason it's liquid is because you kept it at a high temperature. If you break the seal, it will solidify and it will plug the hole. All right? So you have to have really some major act of sabotage to make a hole that won't seal it. But if it does leak out at a big rate, because you've made a big hole, you see all these balls will drop. So you will lose the moderator, just like in a light water reactor will automatically shut off the reactor. So the thing you're afraid of in nuclear reactors, after you shut off the chain reaction, is the heat enough to be removed. The decay heat is, do you have enough pumps to remove the decay heat? And that's just to ensure that you have electricity to run pumps. So I don't know why people in the nuclear industry didn't think of this. Whenever you have a large source of heat, you have a way to make electricity without, you know, a turbine. You know, a thermocouple does it. All right? Many materials can turn a temperature difference into a voltage difference. If you have voltage difference, you can have electricity. All right? So you can always keep the requirements to make pumps work is kilowatt kind of levels. You know, after a shutdown of nuclear reactors, you typically have hundreds of megawatts, so plenty of, as long as you plan for it in advance, okay? So you're not afraid of that either. If you really lose the coolant, of course, then pumps are no use. If you have a loss of coolant, you better be able to cool the fuel in these rods. And that is the unique aspect of molten salt reactors, where the elements are fluid. If you have solid elements, you know, it's very hard to get them out. But with a fluid, all you have to do is to let it drain into somewhere else, into a dump tank, okay, and have it cool passively so that you can prevent it from a serious accident. Okay, let me see how I'm doing on time. I'll try to go quickly. So this has become very popular with the general public, and there's a former NASA employee who has named it, his name is Kirk Sorensen. You can find lots of YouTube video where it's called LIFTR, Liquid Fluoride Thorium Reactor. But I prefer the old name just because I'm at the old age where I remember what things were called. Historically, I still like the name. Two fluid, fuel and coolant, molten salt breeder reactor. And I think most experts that look at this acknowledge that this is the best nuclear reactor if it's possible to build, because it's the only one that can satisfy all the 4 S's, okay, in a relatively straightforward way without operator intervention. So we have patents in the United States, China, Russia, Japan, France, Great Britain, Deutschland, Germany, Sweden, and it's pending in India. Okay, I hope you can, you know, get this through. Let's work on this together. India, you know, is the first nation that should really adopt this technology. Okay, so how do you get the uranium-233s? As Baba recognized, you should use the plutonium that you get from ordinary light water or heavy water reactors and separate it. Okay, this involves a process called reprocessing and put it into the core. You reach a critical mass, the neutrons come out, irradiate the thorium, you get thorium-233, which will typically beta decay to become protactinium-233, which in a well-designed configuration will beta decay rather than capture another neutron to uranium-233. Okay? So in that configuration where the plutonium is in here, it's called a molten salt converter reactor. You can think of it in that as converting plutonium, which you don't really want, but which you have plenty of, into uranium-233. Once you have the uranium-233, you can build a breeder reactor because you get more than 2 nuclei per fission, 1 fission over here, because you have more than 2 neutrons. So one of them you need to sustain the chain reaction. The other one you can use to breed, and if it's more than enough, then you have something extra to go to the next reactor, so you can expand your fleet of molten salt breeder reactors. This was Baba's original vision, okay? And in fact, as you can see, the very same reactor can perform both tasks. You don't need a fast breeder reactor. Now, the advantage is that when you have fission products, their half-lives, the longest lived ones, are typically about 30 years, okay? All the dangerous ones you read about, strontium-90, cesium-137, you know, the longest life. There are a few that are longer, but they just stay with the salt or can be dealt with. The vast majority have half-lives less than 30 years. So if you just put it in the ground for longer than 10 half-lives, it decays to safe levels. So you can ask, is that a difficult task? No. India had that technology thousands of years ago. You're always finding artifacts that are more than 300 years old. China had that, right? Burying something safely for 300 years is not a problem. Burying plutonium, which has a half-life of 24,000 years for 10 half-lives, 240,000 years. No civilization can guarantee it can do that. And that's the problem. Okay, but thorium is easy, all right? You just keep any fissile stuff, you keep putting it through you until it's all gone. Okay? So even though the plutonium is hard to burn up, once you have uranium-233, you use the uranium-233 to burn all those complicated things that I said you produce whenever you try to run the thorium cycle, the plutonium cycle, and so you get rid of all the plutonium in the world. That will make things much safer. Okay, let me quickly go through this. Salts themselves are an interesting chemical problem. Many of you may know that if you have 2 substances, one melts at, let's say, 900 degrees, the other melts at 1,100 degrees. If you put them together in certain combinations called eutectic, the salt can have a lower melting temperature than either one individually, all right? It's a matter of energetics, okay, thermodynamics. It's the same consideration for why alloys are typically better in certain properties than the individual metal constituents. It's a well-known problem in chemistry and chemical engineering. So, for example, we like sodium. Sodium has only 1 isotope. We like fluorine like everybody else. Thorium-23, fluorine-19. Beryllium is also not made by neutron capture, not made in the Big Bang. It's made by cosmic rays busting up carbon, nitrogen, or oxygen into lighter pieces. So it only has 1 isotope, beryllium-9. And those are all very low absorbers of neutrons. The worst one is sodium, but it's not bad, okay? So it won't absorb neutrons, but you can see these are relatively heavy nuclei, all right? So that's important for the next slide. But just note they're all considerably heavier than hydrogen or helium. Okay, so here's a eutectic, but it's too high, all right, in terms of Kelvin. It's not convenient. But here's one that's, you know, about, I think in Celsius, it's about 340 Celsius. You can see it's symmetric about this point. The midway point is a maximum, and it falls at 0.5 sodium and 0.5 beryllium. Whenever you see integers like that, you know quantum mechanics is involved. And I could explain it to you, but it's too difficult. But anyway, take too long. But anyway, they behave, they like to partner in this 1-to-1 ratio in such a way that they behave like a compound. It's really not. It's really a liquid plasma. That's that word. Those of you interested in plasma physics, you know, these are ionized states. That's very important. They're not molecules in the molten state. They're plasma. There's an Na plus and F minus. That means there's no bonds to break. When we have solids and we have hard radiation, we worry about breaking the bonds and change something. There's no bond to break, okay? So they're not affected by all this high energy phenomenon at the centers of reactors. Anyway, if you have a half and half sodium fluoride, beryllium fluoride, you can ask how much thorium can I dissolve in it? And the bad news is you can't dissolve very much thorium without going to very high temperatures. This is the liquidus. Of course, if you do this, but that's very little thorium. All right, so we use a thing where it's 47% sodium by mole fraction, 47 beryllium, and 6% thorium. So what I'll be showing you is something over here. It's almost 200 degrees above where its melting point is. That gives you sufficient room to be able to pump. As you can imagine, the viscosity very close to the melting point must be very high, because it's almost trying to freeze, right? The viscosity of solids is essentially infinite, okay? So you want to be significantly above the melting point. Okay, let's see what else here. Okay, there are challenges to holding molten salts. Oak Ridge did discover an alloy, which is nickel-based, which they called Hastelloy N. It's nuclear qualified to 760 C. So this could hold it here. But it can't hold, you know, if you want to operate the fuel salt up here, it's a problem. But the fuel salt never touches the pool that you want to hold the blanket salt. Okay, so you could use that. We preferred sealed carbon fiber reinforced carbon walls, okay, for reasons I'll explain shortly. But there are alternatives in case it doesn't work. Okay, so here's an interesting fact. Neutrons scattering off nuclei, either 9, beryllium, or 12 times heavier than itself, carbon, or 19, which is fluorine, or 23, which is sodium, heavier than itself. You all know this from physics experiments. When you have something that's very heavy and you bounce something very light, even an elastic collision, you transfer very little momentum to, you change very little the speed of the bouncing off particles, almost like bouncing off something. The velocity is changed, so the momentum is absorbed, but you know, the speed is not very changed. So the kinetic energy remains almost the same. There's a little bit. So the change in the kinetic energy is small per collision. That means it's not like colliding a neutron and a proton. It can lose all its kinetic energy in one bounce. So you can go from 1 MeV in one jump to below the resonances. Here you have to go through the resonances. Okay, so this problem is somewhat challenging from the way nuclear engineers do it. But if you know Chandrasekhar's book on stellar dynamics, you know how to do this problem. And I've read all Chandra's books, okay? So I know how globular clusters, heavy stars, and light stars exchange kinetic energies in a globular cluster. And you know, that ends up with heavy stars sinking toward the center, and etc. So the problem in nuclear physics, as Chandrasekhar realized, right? It's just like Brownian motion of globular clusters, or how cosmic ray acceleration works. You know, if you look at the papers of people who talk about cosmic rays, or how the economists made a mess of the world economy by pricing stocks. There's two things going on. The speed is changing, and the speed times the change, and speed times the change in speed. So one is a drift, what we call dynamical friction in astrophysics. The other is a diffusion in energy space, okay? So stock prices fluctuate. Sometimes they go up, sometimes they go down. But in general, stocks will drift upwards or drift downwards. And so the economists won a Nobel Prize for making this observation. So you say, how's this possible? You know, in physics, we know how to calculate those two coefficients, or the mean over some distribution. How do they calculate in economics? They don't have laws of physics like we do. And they have an assumption. That assumption is that of perfect markets. The market always prices things correctly. So if you believe that, then you have a method. Because 1 millisecond from now, the two coefficients are probably not different from what it is now. So if I have very fast computers, I hire smart physicists or smart astronomers to make this calculation faster than the next guy, I can beat the market. So these guys won the Nobel Prize because they claim to have taken the risk out of investing. Well, all of you can see this is nonsense, right? You can have a sudden black swan event, they call, where the fluctuations are much bigger than any of the models predicted, and it's a death spiral, right, where everything crashes. That's what happened in 2008. So I hope if you learn this, you know, although it will make you employable. Yeah, okay, I'll go through this. Anyway, the reason why I'm going through this is it's possible to make these kind of calculations, if you know astrophysics, by using, breaking this down to a first order partial differential equation in space and energy. If you build a sphere, you can separate the space variable and the energy variable, and then you can make very fast calculations what the distribution function is. So here's the distribution function of this reactor that I told you. It's bimodal. The source is trying to produce very high energy, but as they cascade down, they lower their energy. But the thorium is doing this, so all these thorium lines are depressing the continuum, which would otherwise, and you get this bimodal distribution. That bimodal distribution is important for the nuclear proliferation because for the chain reaction, you rely on these neutrons. For giving you uranium-232, you rely on this reaction. So here's the critical masses. I'll go through very quickly and jump to the end. Okay. So here's safety. Remember I said the worst possible thing is that you lose everything, you lose electricity. Now you've got to dump the fuel into a place where it's passively safe. And so this is what Oak Ridge proposed, a dump tank, but they left out a thing because they were at very low powers. You really need to still take care of the decay heat. And if you have a very powerful reactor, you need it to be clean. So this is a case where you clean it to 1/4 of the normal value. You dump it into 4 spherical tanks where you have buffer salt. So you mix the radioactive salt with the buffer salt so that you can survive the event. So here's what happened. You've got to keep things safe for about a day. So when you dump it, the thermal inertia absorbs it, everything freezes, but the decay heat heats up the temperature until you reach the melting point. So if you're a physicist, you know once you reach the melting point, there's the heat of melting that you've got to overcome before you can increase the temperature again. So here's the enthalpy. It starts at 0, and it gains enthalpy as you heat it under constant temperature and pressure until you reach the melting point. That takes about this is in hours, so it's almost a day. Beyond that point, the temperature can rise again. So the design is such that it never rises higher than this purple curve. If it rises higher than this purple curve, you will destroy the concrete. You know, it'd be like 9/11, the buildings crashing down. You have a little more room to do this. So you design it so it never rises above that. So it will cool down as the decay heat drops until after 3 days or so, it will freeze again. Then you just follow this path in reverse. As you freeze, you release energy, so that helps the decay heat keep things partially molten until over here there's no more latent heat to be released, and it freezes again. So after a week, it has a very slow decline rate. So now you got it frozen, it's not going to move anywhere, so it's completely safe. But after the accident is over, you would like to recover the salt. So what's causing the heat loss? Just black body radiation, right? So to make it molten again, you just cover it up with something that's opaque to cover it with something that's opaque to radiation. You insulate it, you trap the heat. After another week or so, it becomes molten. You can now drop it and pump it, clean it up. So it's impossible for this kind of reactor to have without operator invention even. It's walk-away safe, all right, if you design it properly. You just rely on physics. You don't have to worry about gravity failing. You don't have to worry about temperatures increasing decreasing the density. You don't have to worry about black body radiation. Will happen. Other things will happen too, but that will happen to increase your losses. So let me just show why it's safe, okay? So the worst case nuclear accident for a solid versus liquid fuel is the following. In solid fuel elements, you're afraid of a meltdown. So things that you thought were in place become mobile. You didn't plan for it to become mobile, but it's become mobile. And if the temperature continues to rise, you will vaporize things, you will cause steam explosion, all sorts of bad things that happened in Fukushima and Chernobyl. None of that will happen with a molten salt reactor. Because if the liquid, what you're afraid of in the case of liquid fuel element, is freeze up. But if it freezes up, they become immobile, so they're confined to the plant. If you have enough of an accident, the plant may be unusable, but you don't release large amounts of nuclear radioactivity. And in the best cases, you can recover the plant after 2 weeks. The other thing I think is needed to make it acceptable you have to have transparency. People don't trust the nuclear industry because it seems to be black box, okay? They don't know what's happening. I have to explain it to them. These calculations that I do are so simple. I'm thinking of putting them into an app. I do it with a very low power thing so that kids, instead of playing video games, will design nuclear reactors. It's really not difficult. Superior, secure, sustainable. All right? This was Baba and Indian nuclear physicists. So without the fission fast breeder reactor, you need 3 or 4 doubling times. So how much is a doubling time? The figures I didn't give you. Basically, it's about 29 to 47 years, depending how clean you keep the fuel salt. And so 3 times 29 years is within this century. 4 times 29 is not. But there are always improvements that are possible. So I think it is achievable, but people have to get started fairly quickly. All right? And then you can solve climate change, and then you can use other techniques to reverse climate change. That's the message I want to give to the young people. The world always needs saving. It unfortunately falls on you to save civilization. That is your task. All we can do in my generation is to help give you a tool to solve this problem. And I think astronomers can make big contributions here, okay? So this last thing is convince your friends, your family, nuclear reactors can be made safe, walk away safe, all right? through innate physics, not defense in depth. Thank you.
Thank you, Professor Shu. We do have time for maybe one or two questions. Rita, yes.
I was wondering, in your HR diagram, where do you put the solar energy?
Very good question. So solar energy, as you can imagine, I like solar energy. No astronomer cannot like solar energy, right? In this diagram, solar energy is sort of where you think it would be. It would be between batteries and wood. And the reason is not that solar power is less powerful in some sense, but because solar reactors, like batteries, are complete packages. They include the reactor. I only included the fuel in the other things, okay? So it's kind of an unfair comparison, but once I tell you, you can make the adjustment. So the big problem with solar power is it's just too diffuse, okay? And sometimes at night, you're guaranteed it doesn't shine, and when it's cloudy, it doesn't shine. And that can affect the whole country, okay? So you can never build enough to guarantee that the electricity doesn't stop. But you can use it in tandem with other sources that can supply, back up the solar. Okay, I like solar. It's the one technology. The reason I like it best, it's the one technology that you can scale down. So you can have a calculator that runs on solar power, right? And that gives people, ordinary people, direct participation in this tremendously important task. I think just that psychological reason is why we should continue to push solar power. Wind, I'm less convinced of. California, they love wind, but I think they're a blight on the countryside. Right? They're turning, they rust, and then they don't get replaced. It's an awful, they kill birds. Wind, was one of the first natural phenomena to show to be a nonlinear system that is chaotic. So why would you use a fuel source that's chaotic intrinsically in nature? That seems puzzling to me that so many people like wind.
Okay.
Any other questions?
And we
Okay.
come to since this is an academy lecture, we are giving Professor Shu a memento, which...
Oh, thank you.
Right?
Thank you very much.
These are books.
Thank you very much.
Which,
Books are my favorite object.
Yeah.
Yeah.
That's actually about C.V. Raman.
Oh, good.
It's a biographical material on the founder of the academy.
Good. Yeah, thank you.
So, yes, thanks. We'll get this to your desk.
Okay.
You don't have to carry it. Okay. We then, at least for the astronomers in the audience, we come to the next part of the program, which is I'll request Professor Ramsagar and Dipankar Banerjee to come up. And Professor
Thank you.
Amitabh Joshi, who is the editor of publications of the Academy. And the event which we are looking at is the joint venture between the Astronomical Society of India and the Indian Academy of Sciences to, in future, cooperate in publishing the Journal of Astrophysics and Astronomy. And this is something that's been talked about for a long time, and this kind of, it can only do good to the research publication scene in the country. So
you come up for a joint picture?
yes.
Right. Yeah. Oh, yes.
All of you?
Yeah.
So would you like to say a few things about
Yeah. you don't have to
Hold it
wait
together?
here.
Yeah. Oh, am I supposed to sit down?
You could, please.
No.
Yeah, please. So Professor Shu and other distinguished members of the audience, ladies and gentlemen, it's a great pleasure as editor of publications of the Academy to announce that henceforth the Journal of Astrophysics and Astronomy is going to be jointly published by the Academy and by the Astronomical Society of India. So this journal has been published by the Academy since 1980, whereas the Astronomical Society had been publishing the Bulletin of the Astronomical Society of India, which after this joint publication, I understand that the Bulletin will cease publishing in its present form, but will perhaps continue to come out as a newsletter from time to time. So it was felt that this way, if we could pool these two publications and have a joint publication with the joint weight of the Academy and the Society behind it, it would perhaps be very good for the cause of astronomy and the articles appearing in this journal. And of course, the Academy journals at present are co-published with Springer, as this will continue to be, which sort of adds to the reach of the journals. So I would just like to say that, to place on record that this process of trying to bring about this joint publication agreement began last year with the very active involvement of Professor Ram Ramaswamy, the president of the Academy, and Professor Ajit Kembavi, then the president of the Astronomical Society. And all the details were worked out, and I would particularly like to thank Professor Ram Sagar, the chief editor of the Journal of Astronomy, Astrophysics and Astronomy, Professor Dipankar Banerjee, the secretary of the ASI who is here, and Professor S.K. Pandey, the present president of the ASI, for all their efforts to work out the nitty-gritty details of this co-publishing arrangement and bring it to fruition. And I'm very happy to say that the December 2017 issue of this journal is the first one that is being jointly published by the Astronomical Society and by the Academy. And we are very happy that Professor Frank Shu, a most distinguished astrophysicist, has very kindly agreed to release this first jointly published issue. I would now request Professor Ram Sagar to perhaps say a few words.
Please. I think that's... Yeah, friends, already background is set, so I can only say that you have already seen, this brochure, which provides most of the details. In brief, I can only say that today's event is a very important event in the history of the publication of this journal. Why? Because this journal was initiated, as Professor Joshi mentioned, in 1980 with the initiative of none other than Professor M.K. Venubappu, to whom we all know very well. We all call him as a father of modern optical astronomy in the country, who nurtured not only many institutions, but many observational facilities as well. And he was the first chief editor of this journal and continued till his demise in 1982. After that, other distinguished academicians who nurtured this journal as a chief editor, Professor V. Radhakrishnan from 82 to 87, and then Professor J.C. Bhattacharya from 88 to 91, and after that, it was Professor G. Srinivasan who nurtured from 92 to 2002, and then, Professor Rajaram Nityananda, he shouldered the responsibility during 2002 to 2009, and then Professor Chanda Jog, who was my predecessor during 2010 to 12. So on all these duration, I can only say that our international, this editorial board membership is international. And few metrics I can provide. Most of the things you will find here, which I feel that it's worth mentioning at this occasion, I just looked, I was at least surprised that submissions in the journal during last 3 years, if you see, it's from more than 50 countries. And online submission numbers, of course, slowly it's increasing. It's not very large astronomical in number, but at least there is a positive trend in it. And I'm pretty sure that joining hands with Astronomical Society of India, it will strengthen its visibility and other part of the things. And definitely, there are a few positive things which I would like to mention at this occasion. For example, you see, after online submission, the time taken in from the date of submission to the first report, on an average during last 3 years, if you see, it was around 27 days. Similarly, from acceptance to becomes first time online, average time taken is about 39, 40 days, which is not very large compared to any other international journal. And in addition to that, also, as you know, that it's the first journal published by Academy which has become gone to CAP mode, continuous article publishing mode. It means as soon as the article accepted, it becomes, it gets DOI number and article ID, which become visible to Web of Science as well as to other international community. And on top of all these things, as you know, other journals, reputed journals in the field, they have page charges. At least in this case, there is no page charge, as well as there is no color print charge. So I'm pretty sure that joining hands with Astronomical Society of India, it will boost the activities, and I'm pretty sure the journal will become much more vibrant. Thank you.
I think Professor Ramsagar and Professor Joshi has already said what the background is already there. Just to add, Astronomical Society of India was established in 1972, and today it is the prime association of the professional astronomers. We have about 1,000 members. So one of our main activities are the annual meeting, hosting the annual meetings and promoting astronomy and astrophysics through different activities, including public outreach. And one of our major activity was also this journal, which was a refereed journal, a quarterly journal. But more in recent times, we were observing the quality of submissions were not adequate. I must admit, we had a reasonable, impact factor about 1 all these years, but the submission basically dictates the quality and so on. So some of us senior members like you, junior members are not so young anymore, like me. We were discussing about it for last several years to do a reorganization of this journal, whether it is really worth to have so many journals within a same country for one subject area and so on and so forth. So these ideas were floating around, and exactly at a good time, the proposal came from the academy for joining hands, and it was placed into the journal body, and the journal body gladly accepted this offer. I think now it's a way forward to look ahead and try to revive the quality and keeping the standard international level of competition as well. So I will probably request Professor Joshi and thing to request. Yeah, I can probably coming out together. Yeah, okay.
Somewhere it's hard. Yeah.
I'll wrap it. Okay. Oh, yes.
Brings this, except for the high tea which across the lobby.
Thank you.
We earned out.